Hey chemistry students, this is lesson 11.3 where we take a look at factors affecting solubility.
The first objective is to determine the solubility of a substance and the effect temperature and pressure have on solubility.
Okay, we're going to teach you to define and apply Henry's law.
And to interpret solubility graphs and determine if the solution is saturated, unsaturated, or supersaturated.
Okay, so let's get started.
So we've seen one of these before. It's a solubility curve, a graph. And what we have is the solute per 100 grams of water, and we also have temperature in Celsius. And we're going to take a look at both a solid and a gas. Both of these have different relationships. And for solids, we're all pretty aware of this, that as we increase the temperature on a solid trying to be dissolved, we increase the solubility. Now, something we may not think of very often is for gases. Gases are the opposite of solids. As you increase temperature on a gas trying to dissolve in a liquid, you actually decrease its solubility. This is why a lot of the major fishing areas of the world are found in cold water, because there's a
Cold
higher...
water holds more dissolved oxygen than warm does.
So this is just a trend you need to know for the temperature effect on solubility.
Now that we've taken a look at temperature, let's look at the effect of pressure on solubility. And pressure, you know, how hard the gas above a liquid is pushing down on that liquid does have an effect, but you can see that the effect is different again for solids and liquids dissolved in a liquid solvent than it is for gases. So why don't you explain that, Mr. Hunter?
So as we see above on the graph, you see solubility on the y-axis, pressure on the x. And as you would probably imagine, the pressure above a solution has no effect on how much solid or liquid can affect the amount of solubility. So solids and liquids are not affected by pressure. Whereas gases, as we know, if you increase the pressure above a solution, we're increasing the number of collisions on the surface of the liquid. So in this case, as we increase pressure, we actually also increase our solubility of gas. And they are directly proportional to each other, but
to an extent.
To an extent, yeah.
But we can see that it does start to flatten out up here after a while, but initially as you increase pressure, solubility goes up dramatically. So think of like a bottle of soda. It's got dissolved carbon dioxide in it, and when you have the lid on there and you haven't opened it yet, there is substantial pressure on top of that liquid that's in there, and once you crack the seal on it, you hear the compressed gas escaping, and then you'll see bubbles of carbonation begin to, that's the carbon dioxide escaping solution because you've lowered the pressure over it. So it can't hold as much.
All right, let's go look at the next effect. So up next is Henry's law, and this is just the mathematical description of what we just talked about. Henry's law states that at a given temperature, the solubility of a gas in a liquid is proportional to the partial pressure of the gas above the liquid. Meaning if I increase the pressure of a certain gas, I will increase the solubility of that gas in that liquid. Shown below that Sg, that stands for solubility. The K is a constant that is given per gas type. And no matter what gas you have, there is an individual gas constant. And Pg is the pressure of a specific gas, because in the atmosphere we have more than one type of gas. You can be specific about which type of gas you are talking about. If we're talking about nitrogen dissolving, we'd have a separate K value and a certain partial pressure of nitrogen to talk about.
So you're not looking at the overall pressure pushing down on the liquid, say in the case of nitrogen solubility. We're just looking at collisions of nitrogen atoms with the surface of the liquid is going to keep nitrogen atoms in solution.
Yeah, as opposed to every gas striking. And simplify this law, it states that as the gas is dissolved in a liquid, this law simplifies, states that gas dissolved in a liquid decreases as pressure decreases, or vice versa.
So again, back to our soda thing, when you release the pressure on top of that soda, the carbon dioxide begins to escape.
Yep. All right, let's go to the next slide.
All right, so another effect on dissolving is surface area. So we've got two crystals there. Looks like maybe what is that, copper chloride or something
Sulfate.
like that, copper sulfate. So this one is one gigantic crystal, and here is approximately the same amount finely powdered. Which would dissolve faster and why? Okay, well, if we think back to solution formation happens at the surface of a solid, where the solvent molecules can come in contact with the ions or the molecules of the solute. So this one would have far more surface area because it's broken up into much finer pieces. So I'm going to say that the solubility or the dissolving rate, not the overall solubility, but the speed of dissolving is going to be much faster for that powdered material than for one big chunk of it, just due to the vastly increased surface area.
All right, let's write down that for them. So as surface area goes up, rate also goes up.
So again, this is not going to affect the overall solubility because that's dependent on temperature for a solid, but the maximum amount you can get to dissolve is not related to the size, but the speed, the rate of dissolving is going to be greatly enhanced by powdering up the material.
Yep. Here is a list of solubility rules since we were just talking about solutions. You should take a minute to write the main ones down, which is the ones we have present here. There are certain things that are soluble, certain things that are not soluble, and you need to take a time to write this down.
And we're talking about ions here.
Yes.
So the ion, like what ions are in a compound is going to tell you a lot about its solubility, and we're talking about, again, solubility in
General rules.
water.
Yeah, in
correct?
water and the general rules for that. So take a minute, write down this column and write down the exceptions and all that because it is an important skill to have in chemistry. There's not much more to say on
This
this.
is especially something that you guys are going to hit in AP chemistry next year.
Yeah, and in our chemistry currently for the rest of the year. All right, so here's some definitions we have seen in the past. For solubility, a saturated solution contains as much as it can contain at that temperature and amount of water. So it contains maximum amount of solute. Then we know about unsaturated. That would, of course, be it contains less than the maximum. So, and then supersaturated. And supersaturated is more than the maximum due to a trick that we also discussed earlier in the year. So we won't spend much time on these terms as you should already know them. And then more.
So let's just review how the heck can we get an super saturated solution? If it's saturated as the maximum, how do you get more than the maximum?
Well, we tricked the system, so if you're making sugar crystals, for example, you would boil water, throw in as much sugar as you can to saturate the solution, and then as it cools back down, the amount of sugar stays the same in solution, but the temperature changes. So at that point, you are making a supersaturated solution.
And these tend to be unstable, so things like a crystal falling in, another sugar crystal can trigger like a mass crystallization of the supersaturated solution. But they can exist and do exist. Fudge, if you ever made homemade fudge, is a supersaturated sugar solution, and they put a lot of fat in it that keeps the supersaturated sugar from finding other sugar particles and recrystallizing. If you ever had bad fudge, though, it's got big chunks of sugar in it. And it can start to crystallize. All right.
So here are two questions for you to answer. It's a PVQ. Using the graph on the side here at 60 degrees, is KNO3 saturated, unsaturated, or supersaturated with 100 grams of solute in 100 grams of... I didn't mean to write it like that, did I? Oh, yes,
Yeah,
with 100 grams of solute and 100 grams of water.
Good.
Yeah, we're good to go. And then the second one, determine in each of the following if they're soluble or unsoluble. So potassium sulfide. Yeah, thank you. Potassium sulfide, copper 1 hydroxide, and mercury 2 nitrate, using that table you saw, I think, 3 slides back.
Okay, so we're not using the graph for the second one, you're gonna use the solubility rules.
That's
All right,
exactly right.
give them a try and we'll discuss them in class the next time. See ya.